Propagation. Radio waves, microwaves, and higher frequency waves such as visible light, X-rays, and cosmic rays, and all examples of electromagnetic waves. Propagation looks are how radio waves behave, and once they have left the transmit antenna, radio waves also spread out from the antenna, also shown in figure 7.1. Close to the antenna, they are concentrated, so a receiving antenna will pick up a strong signal further away. The signal will be weaker. Too far away, and the signal will be too weak to be received. The effect is the same as shining a torch beam onto a wall. Close to the wall, there is a clear, bright circle of light. As the torch is moved further away, the light is more spread out and appears weaker. If moved sufficiently far away, it is not visible at all. Radio waves can also be reflected off a large, smooth surface, such as the sea or a side of a building. If it is bigger than a wavelength of the radio wave, refracted in the ionosphere in the same way as the light is bent in a prism or lens. Diffracted or scattered going over or round an edge such as the top of a hill or the side of a large building, tending to partly fill in areas in shadows. Figure 7.1. Radio waves spreading out from the dipole antenna. As the wave spreads over a large area, it gets weaker. Close to the antenna, they are concentrated, so a receiving antenna will pick up a strong signal further away. The signal will be weaker. Too far away, and the signal will be too weak to be received. The effect is the same as shining a torch beam onto a wall. Close to the wall, there is a clear, bright circle of light. As the torch is moved further away, the light is more spread out and appears weaker. If moved sufficiently far away, it is not visible at all. Buildings. Radio waves can penetrate buildings in much the same way as sunlight can penetrate clouds. With radio waves, some of the energy is lost in penetrating the building materials. In a building with several walls to pass through, the signal may be too weak to be of use. Apart from the type and amount of building material, the penetrating building of radio waves is also frequently dependent. For lower frequencies in the medium wave and HF bands, the wavelengths are large and the building appears fairly small in comparison. Such radio waves penetrate buildings relatively easily, but have difficulty in penetrating much larger objects such as mountains. In the VHF-UHF bands, wavelengths are much shorter and the buildings comparatively bigger, making them much more of a problem. At these higher frequencies, the gaps between the buildings are wider than the wavelength of the signal, which can get through the gap as well as being diffracted around corners. However, coverage can be patchy, as might be noticed with a small handheld transceiver or possibly a mobile phone. Inside is less certain. Domestic windows larger than a wavelength will admit a signal, but most commercial glass-sided buildings are coated with a metallized film to reduce the glare of the sun. They tend to reflect radio waves rather than appear transparent to them. Range. The best range with VHF and UHF radio services is achieved when the transmit antenna is mounted high up and clear of local obstructions such as trees and buildings. Outdoor antennas perform much better than indoor ones, which suffer losses through walls and roofs. It helps greatly if the receiving antenna is also placed in a similar way. Broadcast transmitters have very tall masts supporting the antenna for just that reason. It also helps in getting the signal into the dips behind the hills and into the valleys. Such places would otherwise be in a bit of a shadow, although the diffraction over the top of the hill does help to fill it in. Clearly, a more powerful transmitter will have a greater range. However, the effect is not noticeable, as might be expected. Consider the torch beam again. At double the distance, the circle of the light is twice as wide and twice as high. It has 4 times the area to cover. so each bit of wall only gets a quarter of the light. To get the same strength as before, the beam must be 4 times as powerful, not twice. In amateur terms, it is much more effective to use a Yagi antenna outside and above the rooftops to focus all the transmitted power in the right direction than getting a big transmitter. The antenna gain is equally effective while receiving, giving us a more sensitive receiver. A Yagi avoids sending RF in unwanted direction, reducing the likelihood of causing interference. 2. Or receiving interference from amateur stations in those directions. Frequency affects the range. The higher the frequency, the bigger the building and the trees appear to the radio wave, and the more the wave is lost in penetrating them. Hills cause shadows, and the curvature of the earth also has an effect in making any hills in the middle of the path seem taller. At VHF, and even more so at VHF, the range is not much further than line of sight as seen from the antenna, and ignoring small obstructions. Depending on the terrain, that may be anything from 10 or 20 kilometers up to 60 to 80 kilometers in open country from a hilltop. Between handheld radios down amongst buildings, even 1 kilometer may prove difficult. However, from a good location, even the modest powers using CW or SSB ranges of a few hundred kilometers are possible if propagation conditions are good. Weather effects. The weather can affect propagation at higher frequencies. Falling snow, ice, and very heavy rain can attenuate signals, decreasing the achievable range at UHF. Conversely, the range can be greatly extended at VHF and UHF by ducting. This is an effect where a layer of typically warm, moist air traps the radio wave in the layer or duct so it does not spread out much, retaining its strength until the layer fades out, maybe after quite some distance. The ionosphere. The ionosphere is the name given to layers of ionized air occurring at heights between 70 and 400 kilometers above the Earth. Ionization is an effect where ultraviolet light from the sun interacts with gas molecules, making the upper atmosphere. An electron is knocked off the molecule, leaving a free electron which is negatively charged, and a gas ion, which is the remainder of the molecule, carrying a positive charge. The strength or level of ionization depends on a number of factors. Clearly, there is a day-night effect of solar illumination and seasonal variation from summer to winter. Charged particles, typically from sunspots and solar flares, can cause changes perhaps quite suddenly. As the altitude increases, the rate at which the ionosphere naturally deionizes decreases, so higher layers can last overnight. The ionosphere can refract or bend radio waves in the same way as a lens bends light. To see this effect in light, hold a drinking straw at an angle in a glass of water. The straw appears bent at the point it enters the water. In reality, the light is bent as it leaves the water, making the straw look bent. As figure 7.7 shows, radio waves traveling up towards the ionosphere may be bent or refracted back to the Earth's surface, some thousands of kilometers from the transmitter. The polarization of the wave can also change in the ionosphere, which is why polarization of HF antennas is less important. Figure 7.2. The ionosphere can refract radio signals back to Earth as much as 4,000 kilometers away in a single hop. Bouncing off the Earth's surface may allow another hop, extending the distance of a contact. The key point about this is that HF signal can now be heard far over the horizon and well beyond the range that is typical of line of sight, VHF, and UHF communication. VHF and higher frequencies can penetrate the ionosphere, allowing satellite communication and even to the moon. For normal terrestrial communication, these frequencies propagation in the troposphere, which is the region below the ionosphere, frequency and time of day. The time of day has a large effect on radio frequencies that are refracted. When the ionosphere is highly ionized, it can bend higher HF frequencies back to Earth than when it is weak. During the day, frequencies as high as 30 megahertz or more may be returned, whereas during the night, this may be as low as 3 megahertz. In the summer, the highs and lows are more modest. In the winter, the highs are normally higher and the lows lower. The highest frequency that will return to Earth is known as the maximum usable frequency, MUF. As explained, the MUF depends on time of day and the season. The MUF the MUF depends on the particular path and the distance to the receiving station for a given level of ionization. The ionosphere can only bend the wave so much. A close station requires a greater angle of bending, and that might not be achievable. A lower frequency might work better. Amateur radio magazines and websites often give a prediction of the MUF for the month, so the amateur can decide which HF bands offers the best chance of a contact. Ideally, the band chosen should be a bit below MUF. Any one band may only offer contacts for a few hours each day. The band is then said to be open. As the morning progresses, it may be necessary to move up one or two bands until mid or late afternoon, when it may be necessary to come back down a bit. Further moves down in frequency will be needed as the evening and the night progresses. Worldwide propagation is possible by using the ionosphere or sky wave paths. A single hop can travel up to 4,000 kilometers. The radio wave can bounce off the Earth's surface, allowing multiple hops and worldwide coverage. Part of the fun and skill in amateur radio is to know which bands to use at which time and which part of the world it is most likely to get a contact. Sporadic E. Most HF refraction occurs in the higher layers of the ionosphere at altitudes around 300 to 400 kilometers. However, patches of very high ionized air can occur at 100 to 125 kilometers. These patches, sometimes referred to as clouds, occur in a region of the ionosphere known as the E layer and can refract VHF frequencies, including the 2 meter 145 MHz amateur band, less often 70 centimeters 430 MHz. Signals can be returned. Contacts over distances of 2,000 kilometers may be possible, far greater than normal terrestrial propagation. No one knows exactly what causes sporadic E, but as the term implies, it doesn't last long and is difficult to predict when it will happen. Next section will be license conditions, operating practices and procedures.